In this deliverable, our team will present the process of converting the electricity 2D pylon design into 3D one, as well as investigate the results and implications of the extreme scenarios. It will show whether our structure can withstand the various loadings, and we will conclude with overall improvements to the project.
The 3D pylon design was achieved by assembling two identical versions of our 2D cross-sections in parallel relation to each other. It was done by applying the constraints from the challenge description, thus creating a 10 by 10 meter square base. After removing extra zero-force members, we optimized the pylon. Two trusses were linked with stiffening beams on each side. Only diagonal connections were used, as this spread out the horizontal and vertical loads through different elements, giving the pylon more stability. Combining two 2D schemes would give us four separate 5 kN loading points. In order to obtain two 10 kN loading points, the front cross-section had to be tipped towards the pylon's center. The angle at the bottom is 80.5 degrees to the horizontal, and the angle at the top of the pylon is 63.3 degrees to the horizontal. To strengthen the structure, additionally, we added four members to hold the vertices. The pylon took one conish and pyramid-like shape, which adds to the stability and loading resistance of the pylon. Before moving to extreme scenarios, we had to test the construction to see whether it can withstand the load of 10 kN applied on two loading points of the pylon structure. The stress in any of these members did not exceed 5 kN, meaning there was no failure, and so the pylon supports the normal loading.
As observed from the front view, the deformation of our pylon is not significant. Most displacement occurred at the top of the vertices of the structure and does not exceed 1.75 mm, and the rest of the members are not shifting. And the results of the front view can be seen in the side view and the isometric view. In the first scenario, the cable loading is applied at the top points of the pylon, and their magnitude is 10 kN each. There is also wind loading applied from the more mobile right-hand side with a magnitude of 25 newtons per meter. As shown, the greatest displacement is on the top of the pylon, and the bottom part is stable. The displacement did not surpass 1.75 mm, which is an acceptable value for displacement. In comparison to the normal loading, it can be seen that there are members that change from zero-force members to being under tension, and there were also no members undergoing significantly large axial forces. Overall, the deformations are not visible and none of the components face critical failure.
Now the cable loading is applied only from the left-hand side of the pylon with a magnitude of 10 kN. The wind loading is the same as in the scenario 1. Most of the displacement occurs on the left vertex, as this is the place of cable loading. As expected, comparing to scenario 1, there is less overall displacement of the structure. However, because there is no balance of forces, the displacement on the left vertex is bigger than the one from the previous scenario and equals 2.5 mm. The right-hand side of front view scheme deforms slightly and goes under tension. The side on which the force is applied changes from minus 2.5 kN to minus 5 kN, hence the compression is greater. The deformations are somewhat significant but not causing the failure. The pylon tilts to the left and is bulking. Thus, when making improvements to the design, the thickness of front view, left and right members must be enhanced.
In this scenario, both the wind and the load are applied on the right-hand side of the pylon with equal magnitudes to scenario 2. The direction of tendency of the deformation is opposite to that in scenario 2, with most of the deformation taking place towards the right-hand side. Most of the deformation takes place in the upper right triangular structure. Stress distribution is similar to that in scenario 2, but with an increase in compression on the right-hand side members, where the force is applied, and a decrease in the tension of the internal triangular components of the structure. The deformation observed in this scenario is the largest out of all the scenarios that have been shown up to the moment, with the pylon leaning significantly to the right. Nevertheless, the risk of failure is minimal.
Lastly, in scenario 4, we examined the effects of the removal of one of the roller supports due to a car collision. Most components of the pylon, which were stationary under normal load conditions, have now experienced a displacement of approximately 0.5 mm. Stresses throughout the structure are very similar to the normal case, except for the vertical members at the back on the right-hand side. The compression within this member shifted from 2 kN to 12 kN, as they shifted to support the moment and the forces without the removed member. Overall, the total deformation of the pylon component is small, and even in this extreme case, our design proved largely resilient to deformation, and the risk of failure is small.
In conclusion, further iterations of our design must target the wire supporting vertices, as well as the lowest horizontal section, both of which deformed somewhat in all of the scenarios. These can either be redesigned entirely, or some of the members of these sections can be modeled to have a larger cross-section.